start with talk linear regression with something called least square, the objective function, and talk about the algorithm for learning parameters models, right? So far, and we talk about a certain way to learn the parameter models within the base classifier, and either through the assumptions of the naive Bayes assumption, or through the Gaussian assumption. We learn the parameters. So, but those parameter learning is relatively simple, right? So we essentially estimate them in one shot. So in general, we might need to more sophisticated methodology and estimate those parameters iteratively. And now we're going to talk about something called a gradient descent methodology for learning parameters of the linear regression models. Okay, and then there are a few other things, topics I'd like to go over them here. So let's start with the fundamentals here. So this is more or less go back to the fundamental frameworks for supervised learning. So right now we will start with the regression, and then we talk about classification. So the supervised learning here. So there are a few steps, and usually we will go over them. So in general, they can be distinguished by this. So start with the data. So the first thing we need to understand is this. We need to be clear about what kind of data we have. And that usually in the forms of training data set that is offered to you. So in our cases here, our data sets here, typically, the way I write them is writing in notation in this way. I hope you can get familiar with this line notations here. Usually I write it in this way, X superscript I here, and Y superscript I. So I usually written in this representations here. And so the superscript I represent the index of the samples. And which sample are we referring to? And usually I goes from 1 to m. So m is the total number of samples we have in the entire training data sets. So usually we write down in this way. So which means, right? So you have m training data sets. Each one of them with input is x, the output is target value is y here. So in general, we're going to make this assumption here, xi here is n-dimensional. We're going to assume it's n-dimensional here. So which means that the input data will have contained n features. N features here. Y here is the target, this is the input here. And then the target y, so it depends on the types of problem we have. It might be a continuous number for regression problem, or could it be a categorical number for classification problem. But for now, we're gonna start with regression problem. And for that reason, I'm gonna assume y will be a number, continuous number. Now think about it, maybe give a specific example. You can think about, try to predict the rainfall in the amount of rainfall in urban. So that would be continuous quantity, either 0 or a certain amount, how many inches they have, right? Depends on other features we have. So this is a general case. We're gonna start with data. We make clear what kind of data we have here. Features we have, what the target value we're trying to predict. So that will be the first step. And then the next step will be the models. So that will be the second component now. This is a model. And which model should I choose? And these are usually the assumptions that we're going to impose on the underlying models of that. And in particular, within this lecture, we can assume models to be linear. Essentially, we can talk about what I mean here. Essentially, we have a set of parameters here that tells you the weights associated with each individual features. And then we're going to combine those weights, combine the features through weighted summations of the features here with the weight specified by this parameter theta. And that's my model. So usually for different machine learning model, we have different models. You can think about linear regression, they have linear models here, and neural nets, that would be nonlinear models, or decision trees would be different types of models. And the third, this is if I want to put a kind of index here, this would be first component. We need to be careless. We need to be very clear about. The second component is the model. And the third component is something called a loss function. Essentially, in this part here, we need to have come up with a metric to evaluate the performance of the models. And this metric here is not the same as what's the accuracy or error rate of your models. And then this is something we have to come up with this model such that we can learn the parameters based on these objective functions. And in many cases, we call this type of the evaluation metric here either called objective function or called a loss function. So different people sometimes use different terminology, but they're referring to the same thing. Or sometimes you refer to the energy function, but that means the same thing here. So we're going to use those terms interchangeably, either use objective function or loss function. Okay. So this is essentially the metric to evaluate the performance of your models. Essentially, evaluate this particular choice of the parameter here. And usually we formulate them as a loss function, which try to evaluate the inconsistency between your model prediction and your ground truth values, annotations. So that's the reason, more specifically, we say is a loss function. The reason we use loss function because now when I try to choose the parameters here, that will be the next step of that. Within the next step, I need to identify the optimal parameters, and that, in different community, in the mathematics, we call it optimization. In machine learning, we call it learning algorithm. So the algorithm try to identify the parameters here. So within this case here, we formulate as try to improve performance. And if I say formulate as loss function, I try to minimize this loss function. So it depends on how do we formulate it. And then the optimization in terms of improving performance could be to minimize the loss function and to maximize the likelihood function, right? But overall, we're trying to say minimization process. So that's the reason we formulated the object function as a loss function. Okay, so that's something we're going to stick with. So that's the general framework. Let's think about in this particular framework of linear regression, what does this look like here? So here shows you some of the examples for simplicity. I'm assuming the features here is one dimension. X here, one dimension. Okay, so one dimensional simple linear regression. And the red dots here represent my training data sets. Essentially, I have the data set here, here, and so on. This is my targeted values here, Y. And I want to learn a linear model to explain the data here. So under the linear model here, my predictions here is simply the Y. I use this notation here. Y hat is my prediction. So under this linear model, my prediction here is simply said to be linear combinations of the input features here plus a bias term. Theta 1 times x1 plus theta 2 times x2 plus then, within this framework is simple, right? So you just have theta times x here because this is one dimension here. So there are two sets of parameters here. This is something called a bias term. And this is a slope. If you look at this a line here, so this guy's here will be theta. Right, this is theta 1 here. That will be slope of that. The intercept here, this point here will be theta 0. So in order to specify a line, you just specify the slope of the line and also the intercept of the line here. So that's the reason you have two parameters, the bias and the slope here. And that will be the so-called simple linear regression with only one feature.